So, hello, everyone. This is Chuxu. Welcome to our tutorial. So, I'm going to play our pre-recorded videos. If you have any questions, please post them on the chat room. So, let's get it started.
So I'm Nitesh Chawla. Notre Dame and recently graduated and starting his new tenure-track position at Brandeis. Meng Jiang at Notre Dame, Xiangliang Zhang at King Abdullah University of Science and Technology, Yanfang at Case Western Reserve University. And we would be collectively trying to talk about a variety of theoretical fundamental topics within multimodal network representation learning, as well as different applications. So general outline of the tutorial would be, we are in the part 1 right now, and which, so I'll give you a very brief introduction and overview, but the meat of the tutorial would largely be driven by Chuxu, Meng, Xiangliang, and Yanfang or Fanny for the rest of the duration. And we have split the tutorial into multiple parts, where part 2 would be unsupervised methods and applications, part 3 would be semi-supervised methods and applications, and finally, part 4 would be unsupervised methods and applications. So our goal is that we can cover the gamut of multimodal representation learning from unsupervised all the way to supervised learning, as well as their applications. So as we think about multimodal data, what does that really mean, right? So today, if you think about data that's coming with different context, it's whether the spatio-temporal context, if you think about our network, who's communicating, when somebody's communicating, how somebody's communicating, where somebody communicated from, what somebody communicated, what content it was. So one can imagine this to be extremely multimodal and heterogeneous, where you have the actors, you have the locations, you have the timestamps, as well as the content that's going in. And one can think about the video, audio, speech, even from that perspective, right? As one is collecting that data. One can think about different network or graph data, whether if you imagine that is the typical, a very popular data set that we have used within the domain of heterogeneous graphs and multimodal data, is the DBLP author or ONIT minor author data, or the Microsoft Academic Scholar data, where we know this is an organization, this is an author who belongs to this organization, this author authors this paper, and that paper is then published in some venue. And then there are these different connections of different nodes, paper, author, organization, venue, etc. So this is the multimodality, if you will. This is the heterogeneity within the data. And as well as if you imagine an e-commerce site, whether it's the image of a clock, or the description, or the reviews, and the cost that's attached to it, and what are the attributes that there may be. So as we imagine this, that this kind of a data that's coming in, how do we now extract the structure from this data? If we think of it as a network data, what is the connectivity among individuals or entities in the network, whether it's authors, papers, or it's a product like a shoe, or it's a product, two products connected with an individual, as well as the content that may be inherent in this network, whether it's the text of the papers, or whether it's the social media posting, or it's the image associated with the product, or it's the reviews associated with the product. How do we truly pull all these things together are an interesting caveat. And we would be looking at all of these things, and how do we not only extract and model the structure, but as well as how do we extract and model the content with the structure. So essentially in this tutorial, again, just to summarize, the methods would be, we would be looking at different embedding methods, right? Whether it's the attributed network, heterogeneous network, heterogeneous graph neural network methods, or we would be looking at learning approaches on these, from generative model learning all the way to deep learning approaches, as well as matrix factorization and learning to rank, and complementarity learning, and looking at applications of these topics. And the applications include decision-making, and we'll be contextualizing these within the relevant data of these applications. Recommendation system, whether it's an academic system, what paper I should read, or a product I should look at, or a cybersecurity and health intelligence. When I'm thinking about cybersecurity, whether it's what malware exists, or what I should not download, or what app could be a risk for me, and as well as what healthcare applications there may exist. And finally, graph alignment as well, as an application. And we'll be looking at each and every one of those. So that's I would be wrapping up the part one of what this tutorial would be about. And again, the goal is that by the end of it, I hope that we have an understanding of what ways we can begin to model this data, whether we have labels or we don't have labels, or we have partial labels, and what applications within those contexts we can deal with, and how do we sort of look at the data and then map it to a learning problem. And then hopefully you can apply these to some of your own research topics from that perspective. Again, thank you. And I hope you enjoy the rest of the tutorial and ask us a lot of questions. And that's what would make it more fun and interactive. Thank you.
Hello, everybody. My name is Meng. I am an assistant professor at the Department of Computer Science and Engineering in University of Notre Dame. So I'll talk about user and behavior modeling methods with multimodal data. So first of all, what is behavior modeling? Behavior has multiple kinds of components. Behavior modeling can support a variety of applications, like in social network, in the web services, or e-commerce, the shopping platforms. So the components of behaviors include, behavior intentions. For example, we may have different kinds of intention, like we are looking for interesting information on social media. But we also have suspicious users like fraudsters or spammers on the web to, manipulate the information. We also have fake accounts and fake information, fake news on the web. And the second thing is social context. This is very important for understanding the user's decisions, right? So you may be, your decisions are influenced by your relatives, your friends, or your social connections. And so then social context which can be formulated as a network data. The learning on this kind of social context will be really, really important. The third thing is spatial temporal information. Because at different time, different place, we make different decisions. We do different things. And the last one is behavior content. Like we post the text, we post the images and share videos on the internet. So those contents are either grid data or unstructured data. So how can we mine knowledge or build models to understand the content is very important. So based on these four components, I'd like to discuss like 3 examples of behaviors that may create multimodal data. The first kind of behavior is social media content generation behavior. Like we post the content, we share content on social media. This one is a post by the Notre Dame Fighting Irish. So you can see it has a user profile, you can have a user profile information, you have a social network like I am a friend of this page or say a follower of this page, and you may have text of this post, like, you know, it could be multilingual, even multilingual, like have the multi language text. And it may have emojis, has, you know, words, phrases, hashtags. A post can have images and videos. So all this will form multimodal content data and also show social data. So building, we want to build a representation learning algorithms to learn the representations of the users, of the content, to predict the user behaviors. For example, who will like what, who will dislike what, who will love what kind of things, those kind of behavior on a social network, so that we can recommend content or do target advertisement. And the commenting behavior, sharing behavior, and posting behavior also will have influence on the information propagation on the social network. So those kind of supervisory information can be used to train your representation learning model from the raw data. I mean, the raw multimodal data, image and text and users and network. So second example is this kind of, I call it referential behavior. So on Twitter, for example, you can retweet something and put out comments. Like here, you know, the president of the United States can retweet the 2 different kinds of posts and adding his comments to that, and either positive or negative. So for this kind of behavior, we may have the social network. We have the user profile. We also have information source. Where does this come? The referred content come from? Referred content come from, for example, from Nepal, from this person called Dan. And we have multiple kinds of modalities content, like, you know, the text, the images, and videos. So then again, we try to build representation learning models to predict like the sentiment of the post. It's a more like a angry post, it's a happy post, or predict the stance, right, positive or negative, to what kind of opinion, and also try to predict the intention of adding such kind of a comment, or citing the content, or commenting the content in the internet. So this is another kind of behavior. Citing behavior is quite common in academia. So this is also a kind of a referential behavior. For example, when we, as an author, we write a paper. When we write something, we can call that thing, the sentences, we call those generate content, GC. Okay, we generate those contents. And in our content, the content we generated, we refer to some content that we cite, right? We cite those content, we call it referred content, RC. For example, the left hand is a social media example, right? So a user can retweet something, and we call the original tweet RC. It's a referred content. And the added comment, we call the generate content, GC. So when we write a paper, the citation, right? So for example, this paper set the numbers 19. So that number 19 paper, you can go to the list of the references and find the original paper. So that content of the paper is the RC. They refer to the abstract, to the full text of this paper, and add a sentence in this author's own paper. So this sentence, we can call it generate content, the GC. So this is a kind of citing behavior or referential behavior. So, modeling this kind of behavior for predicting the stance, the sentiment, the intention is also very interesting. The last kind of behavior example is collaboration behavior, right? When we form teams to achieve a goal, the same goal, right? Forming team and do some problem solving. In academia, it's quite common, right? We have co-authors, collaborators working together to solve the problem and publish a paper. So we may have multiple dimensions. We have the researchers, we have the affiliations people come from, their publication records, which means that the history of their research, and the text of the content, like, you know, the keywords, abstract, and full text. We can even try multimodal. For example, we may have figures and tables and even references of the paper as a context of this behavior, right? Context of behavior. And this is multimodal data. Again, we try to build representation learning models to predict whether the paper will be accepted or rejected by the conference, or which kind of venue, conference or journal, that this paper will be published. And also whether this paper will be this joint work, this kind of teaming behavior will be successful or not. One way that we can use to measure the success of a behavior, a teaming behavior, is number of citations of the outcome. How many times it can be cited by other works. If it has more citations, likely it's more impactful. We can use this kind of signals as supervisory information to train the representation learning model. So the challenges in modeling this kind of multimodal data generated by users from their behaviors is, one thing is processing. Right? We have to rely on multimodal encoders. The encoders will transform the raw data into vector representations. For example, the text encoders, we can try language models, the graph encoders, or image encoders. And the second challenge is on learning. How can we learn the interactions between the modality, right? The interaction across modality, for example, the text and image, the complementary between these two kinds of information, and also social network and their sentiment and their the text and the image they post, and also emojis. So there's also the graph and the text may be complementary. The last one is optimizing, right? For different kind of application or the task, like those three kinds of examples, we may have different kinds of objectives to learn the representations. Okay, so in this tutorial, I want to present two examples, two work. One is a work that use multimodal data to identify the intention of referential behavior. This work is published in the Web Conference 2020. And the second work is using multimodal data, multidimensional data to predict the success rate of project teaming. This is published in KDD 2019. Okay, let's come to the first one. For referential behavior, like you can see here on social network or academia, the related work is trying to understand the generic content for predicting the stance or the sentiment. Like here, one domain is called stance detection, that is to identify the author's stance in this generic content, say it's positive or neutral or negative to the referred content. And the second domain is sentiment analysis, that is trying to identify the polarity of the author's sentiment. It's more happy or sad. However, we find that the referential intention, which means that the why did the author or why did the user retweet something or write or cite that paper, right? What is that intention that they make this kind of a referential behavior? It's not only about that author's sentiment or that author's stance. Okay, for example, here, say this user said Obama is truly amazing. Right? From just the content, probably you'll extract the bag of words, and you can use a sentiment analysis to make a prediction, and eventually you got the answer that is positive and happy, right? This author. But if you just use this kind of sentiment to conclude the intention of this behavior, you say, oh, actually, because this user is very happy and positive, either to the reference content or to Obama, whatever. So that could be wrong because this user was not positive or happy with that referred content. So he actually retweeted the President Trump's tweets about the stock market, where the President of the United States thanks himself for making that the stock market surprisingly good. So actually, if you just do sentiment analysis, you cannot capture the intention of that retweet of that user. Actually, that user is rejecting. Okay, it's not accepting the original content or the referred content. He's actually rejecting the content. Okay, with a positive words, a set of positive words like truly amazing or credits. So this shows that the intention is not equivalent with sentiment or stance. Another example, I assume that most of you are familiar with network embedding, network representation learning. These two works are very renowned, right? One is Notre, published in KDD 16. The other is LINE. It's Large Information Network Embedding in Chuxu 15. So in the paper of Notre, the authors describe or say cite the work of LINE twice, more than twice actually. One of the times they say when they hold a positive stance when they describe the impact of network representation learning, because Notre is also doing network learning, right? Network representation learning. So they want to talk about the impact of this kind of research direction, which the LINE is also in the domain, in that field. So at that kind of case, the authors, hold a positive stance with the work of LINE. But on the other side, in the related work, when they describe the uniqueness and the advantage of the proposed work, I mean, Notre, so they have to compare with LINE to show what are the weak points of the previous work, right? So they hold a negative stance, talk about like either scalability or some other kinds of weak points that they address in Notre, flexibility, like that. So yeah, why did the authors have different stances to the same thing, right? They may have different stances to the same thing, positive or negative. It totally depends on the context, right? It's not just about the stance, it also depends on the context. So that is intention, okay? Given different contexts, you may have different kinds of intention, right? So in this work, these authors try to understand why a user refer to a content, that intention. So they find that for a certain kind of opinion, the authors may have a stance, positive or negative or neutral. And they assume that the readers may also have a stance, right? Positive or negative or neutral. So what the author tries to do, or the users tries to do in their comments or in their generic content, is to make the readers agree with them, okay? Agree with them, putting that in the literature. So if the readers hold a positive opinion that is that the author is also feeling positive, then they just have to accept this kind of a case, right? They agree with the readers. So if the reader hold a negative idea about that referred content, then the author will try to use very strong words to say, actually, the referred content should be accepted. Should be accepted. For example, if the readers, they assume that the readers are more against something, but now the author said it and feel that it's actually a positive thing, then they have to make the a very strong intention of this kind of, I call it strong accept. When everything comes to neutral, when the author holds a neutral idea, then it's actually describing the background knowledge of the work. And when the author is negative with a certain content, I mean the referred content, if the readers is positive or either negative, they try to be strong rejecting the referred content. Okay, this looks very unclear, but let me give you examples. You will see the three types of instance. How does that in 2 dimensions lead to 4 kinds of behavior intention? Actually, this kind of 4 kinds of behavior intention were formed by a work in behavior sciences. So here are some examples. For the strong accept, you can see that here, when the on the left-hand side, when these papers cite the 22, which is actually the Word-to-Vec work, right? It's a Word-to-Vec. When it talks about, say, actually the Word-to-Vec can outperform several previous approach, they assume that the readers has not that learned much about Word-to-Vec, right? So they try to use a very strong accept wording to show their intentions. We strongly accept the Word-to-Vec, this referred content in their work. So the second type is accept, right? When they cite this number 17, and so they talk about this SVD. Well, the they may assume that the readers know SVD very well. Okay, SVD very well. How to use matrix factorization, which was published in 2014, for feature extraction. And they assume that readers know this work, and they feel already positive with that, while the users, the authors, they accept because they used, right? You can see here, they used SVD in their work as like a pre-processing on the data. So they say, okay, we accept this work, this number 17. They don't have to say we strongly accept, because they don't have to talk about how this existing work, this SVD outperforming other approach, because they assume that people have to know this work very well. A third type of intention is background, that is describing the background knowledge of the work or in the domain. Okay, and last one is strong reject, when in the related work they discuss the shortcoming. You can see here major shortcoming, right? The weak points or the shortcomings of the existing work. Try to do some comparative analysis, because they may assume that the readers accept the existing work, know their strong points, but now they want to say, actually, our work is much better because we address the weak points of the existing work. So the authors will would talk about how they strongly reject some features of the existing work. Right? They'll talk about the shortcomings and weak points. Okay, to predict this kind of behavior intention can be really, really useful for many kinds of applications. But how can we do that, right? From the data side, actually, we have multimodal data. We have the textual data, we have the generic content. We also have another kind of textual data that is the referred content, right? The content of the cited paper. And we have the network context. This is graph data, right? Or we call it network context. It's a heterogeneous network of the paper nodes and author nodes, venue nodes. And also in the generic content, we have different parts, right? The sentence that have this trigger of the citation, this sentence, we call it local context. And the neighboring context, either the former sentence or the later sentence, can also play a significant role in reflecting the intention of the author, right? So just this kind of user-generated content or this author-generated content can be split into three parts: the neighboring context former, neighboring context later, and the local context. So now we have four kinds of, five. We have five modality, right? We have five kinds of information that will fuse together to make the prediction on the behavior intention. The proposed framework is actually we can use multimodal encoders. We can use language models to process the textual input, like the neighboring context, the former, local context, the neighboring context later, and the referred context, referred content. So through that local language model, we can perform a local attention on the sequence data. On the other side, if the input is network data, we'll use a heterogeneous GNN to perform a graph attention to find the most important part of the data. And then in this novel mechanism, it's just called interactive hierarchical attention, that is to model interactions between the modalities. Like here, it has a cross, between the neighboring context and the local context, or the local context and the referred content, and the referred content and the network context, and eventually having a global attention on all the kind of interactions of the modalities. So here for the multimodal encoders, this is one component of the framework. It models the textual content, model the network content, context, and it has an interactive hierarchical attention mechanism and global attention. To model the interactions of the modalities, you can see here, say the reason, right? It's an intuition of modeling the interactions, like why do we have the interaction between the local context and the neighboring context? Why do we concatenate them together and perform attention, right? And the referred contents and local contents, because they are tightly related to the same topic, so we put them together. And also referred contents or the local contents, they were produced by a pair of linked nodes in the network context, because you have got network data and it has two paper nodes. One is your this author's paper, which is local content, and the other is the referred content come from, where the referred content from is a paper node, another paper node. Right? This when it cites, they are cited, they are connected. So RC and NetC, which are the referred content and the network context should be interacted, and the local context and the network context should be interacted. So the data here is we collected like 40 papers from 2 popular research topics, which were published in the data science or data mining or machine learning conferences, and then labeled the 1,500 citations in total. When we say citation, it's actually the triggers. For each, we allocated on the sentence level. For that sentence, if there's a bracket down there citing a paper, what's the intention here, right? We have experts to understand. We have recruited 5 annotators to do the work. So for the social media, we do the same thing, right? We got the news and the retweets. So retweets can be considered as referred behavior. What are the comments of to the news articles? And then we label the 400 referential behaviors. So probably you can see here in academic data, background citations are the majority, because we have related work sections, right? And then a strong rejected is the second most, because we researchers always try to compare with the existing work. And the strong rejecting is the majority in social media, right? Because only when you got a really strong opinion, usually it's rejecting the original content. You feel that you should send this kind of information to your this opinion to your audience, to your friends, to your followers. So that's why you post a message or retweet a message on social media. So that's why this strong reject is actually the majority. Okay. So we compare with the existing work using our proposed interactive hierarchical attention. You can see the accuracy and F1 score improved both on the academic data and the social media data. Okay. And we do evaluation study to show that each kind of context can be really useful. Okay, useful for the prediction. And for all types of the behavior, we can see that this proposed IHA is the best curve down here. While for the background, the improvement is not very significant, because it's kind of an easier task. Okay. To know that it's actually neutral about the background. While for accept or strong reject, it's a bit more difficult. So that's why our framework performed much better. Okay, the next work is predicting the success rate of teaming. For teaming, let's see here, why do we do representation learning, right? Say, given a team, what is a team, right? They got not just the team members, but also the context. Like, it's also one kind of very important question from my students. Sometimes they ask me, say, okay, we got this kind of idea, and should we invite external collaborators on the team to do the work so that we can be more effective, so that we can target higher conference or higher reputed journals? How can we answer this kind of question? Okay. So you can see here the team may have the authors, the blue things down here. We are looking for the collaborators and some keywords that we are constraining the research work topic that you are interested in, and there's some reference, which means that the papers the students have already read and interested. So now the student get a goal, right? Aiming goal, that is the venue. So I want to publish in KDD, which is a top tier conference as a very ideal outcome of the project. So what we can do is to learn the representation of each component, the reference, the keyword, the author, and put all together, aggregate it together as a project embedding or representation, and put into a predictive model and see whether we can predict the outcome, if it will be accepted by the venue or not, right? So that's why we do representation learning because the dimensionality of the data space is huge. We have to project them into a low dimensional space for efficiency. The related work is trying to model or to measure the similarity in the learning. For example, here in some of the work, they try to understand, okay, how many common neighbors you have, how many connections you have between the two nodes. If they got more neighbors, more connections, then they are more similar, or say their distance is smaller. So we can use this kind of observation to optimize the representation of the nodes in the low dimensional space, okay? But for teaming, similarity is not a key. Think that, do I really want to have, or do the student really want to have an external collaborator who got very similar with us? For example, if that collaborator is similar with my student, then that will be just another junior graduate, which cannot improve the effectiveness. And if the collaborator has very similar knowledge or skills with me, he or she can still not improve the effectiveness of the project. The only thing we are looking for is someone who got complementary skills and knowledge that can improve this team, right, toward the goal. So we realize that the members are expected to have complementary skills in a successful project. For example, you got 4 persons in the project: red, green, blue, yellow. So the similarity learning will just learn their potential based on their characteristics or the skills. The red will put together, blue to put together, and then you learn the representation. Then you'll be cast together. So that's not a good objective for this application. What we propose is to preserve the complementary relationship in this context between all these components from the data. So if we can represent the goal, for example, the value, say KDD, as a data point in the vector space, as this kind of success point, okay, then every paper can be considered, or project can be considered as a starting from home, from the original point, to add more context, more component down here. The right person joined us, another keyword joined the context, or we have another collaborator, and eventually try to approach the success point, right? So then if they put together can approach the success point much better, closer, then we know that they are more complementary with each other. So this can be used to optimize the representation of the components of the behavior. So how can we do that, right? If we have the vectors of the context items, or the components of the plan, and we have the goal point also represented in the vector space, the thing we want to optimize is like we should have an observable measurement to describe the plan effectiveness. So suppose the goal point is down here as this G point, and putting all the context together, we got this plan, the second plan P2, and we may also have this first plan P1, right? How can we measure the effectiveness of plan P1 or plan P2 toward the goal G? Okay, so one idea is just use a distance, right? You can draw a circle around G. Say if the plan is closer to G, then it's more successful. However, we realize that goal has a very special characteristic, that is, we may do better than the goal itself, right? So for example, it can publish in KDD, but it can also be a highly cited paper, which is accepted in KDD. It can also be a best paper or best paper mentioned, honorably mentioned paper. So the goal should be represented as a ray. You can see here, starting from this point, it's a ray down here. And the distance is like, should be measuring this way. Say if the plan, the point of this plan is on this curve, then we use a distance, the Euclidean distance. However, if the plan is like this P2 down here, then we'll just use a distance from the plan to the ray, which is this epsilon. So that's how we use a distance, this kind of distance to to measure the distance to success, okay? And you can see the shape is quite interesting. We call it tube, right? It looks like a tube. So once we are able to measure the plan effectiveness, then we can optimize the representation of the plan, including the representations of the components of this plan and the representation of the goal, right, all together. We can sample the negatives. For example, we just switch some, shuffle some components of the plan. Then we assume that they will not be able to achieve the goal anymore. Then we can still do this kind of learning. Because we only, from the data, we can only collect the successful samples, right? Positive samples. Because all those papers in the public data sets are always accepted papers, not rejected papers. So we have to do sampling to generate some negative samples. Once we are able to learn the representation of the context items of the plan and the goal itself, then we can measure the complementary of a component CI and component CJ in a plan toward a goal, right? So here, suppose we already got a plan P prime, and if we have PI, we can be here, a little bit closer to G. If we have CJ, we can be here, also a little bit closer to G. If we have both, we'll be here, right? More close to G. So the complementary should be, say, suppose we only have one of them. What is the smallest distance we have, right? Well, if we have both of them, are we going to have smaller distance? If yes, then we have a positive complementary, right? Because when we have both on the team, we can do better. So that's how we can measure the complementary between these two things. You will see that they are different from similarity, right? When you do the measurement. Evaluation on the synthetic data, we did a quite interesting experience. That is, we generate the synthetic data. This is more like a gaming. So because my students like this kind of a scenario. Suppose we have five players. Okay, they're like the team members. Okay, team members. So each of them may have the skills. So suppose we have 3 kinds of skills. It's just more like the dimensions of latent space, of the embedding space. The skill ABC could be like offense, defense, and like wisdom, something like magic, right? So each player may have a representation of the skill, okay, on the skills. So it has 2 offense points and 1 defense points, the 2A and 1B are the skills of this player. And we randomly just assign the skill points to the users, okay, to these users. So those can be considered as a latent representation of the users. And then if they form a team, these 5 players form a team, then we assume that the behavior plan, which is like the strength of the team, is a summation of the skills on each of the dimension, right? So totally, the team will have 5A, 6B, and 2C. And this team is going to achieve a goal, or say earn a badge, and that badge is, suppose it's AB, capital AB. And if you want to earn a badge A, you need 5 A points. Need B, you need 5 B points. So this team will be able to get an AB. It's gonna be a successful team, right? Because it has 5A and 6B. So you can eventually have AB as a goal. We generate with synthetic data, right? So we generate some players and randomly put all them together as a team. Like see here, you can see the number of skills we may have. We generate multiple kinds of data on different numbers of skills and the different number of goals, and different number, a really big number of the plans when we have more skills, right? The valid behavior means that the successful, I would say positive behaviors eventually we have. So based on that, we can learn the representation of the players and the goals, right? The goals. And we can see here, the quite interesting is the representation of a player who got 1A and 1B is exactly the summation of the representation of a player who got 1A and another player who got a 1B. So you can see here the skill dimensions were successfully learned by our algorithm. Right? We didn't let the algorithm know that the skill distributions at all. We just know the pairs of the player set and the goal. Okay, we have no idea about the skills at all. And they try to learn the latent representation, and we find that this latent representation matches the skills very well. And also for the goals, it's very similar. I see here, the GAB is like 5 times longer than the player who has 1 A point and 1 B point. Okay. So we also tried our algorithms on academic data. We hold out one component, for example, one author or one keyword or one reference, and make a prediction. Also, we try to hold the label out, which is the value, right? We hold the outcome, the goal out, and make the prediction. So you can see here, we use recall at 10 and the harmonic mean of ranks as a measurement. So here means, this ranks means the choose, right? The rank of the choose in your prediction. You ranked all the values, for example, all the values here, and which where is the choose? Where's the choose? So the existing methods like the this line or no2vec may rank the choose the value choose at maybe top 50 or top 67, but we can put it on top 12, right? Top 12 among 2,000. There are 2,000 possible values. We can put a choose at the top 12. And for the authors, we the set is really big, right? Among the 100,000 authors, the similarity-based methods can predict the choose authors at around like 400, but we can put it at 59, the top 59. Also for keyword and references, perform pretty well. And then say we only we have this kind of a factor called gamma in the algorithm, but we are not observing the gamma, right? We just use an epsilon. Say if it's accepted, then epsilon is 0, but it's not accepted, then epsilon is bigger. So what is the gamma in the data, right? After we learn the representations, does the gamma play a significant role? So we look at the papers after we learn, right? So we can measure the success rate of the papers. So if the gamma is bigger, it's more successful. And if gamma is smaller, so small list will still be accepted is 1, right? The small list, but still be accepted is 1. But the bigger gamma could be really big, 100 or 50 or whatever. So here we take the 5 highest success rated, 5 biggest gamma, and the 5 lowest gamma, the papers. And then for each year, okay, for each year, and we go to Google Scholar to look at their citations, and we find that most of the time the bigger gamma will have more citations than smaller gamma in the same year. So you can see, yeah, the red one is higher than the blue one. Well, yeah, because from the time goes on, the very recent papers may have fewer citations. So that's why you'll see it's going down, okay? A case study showing here is, you can see this paper, right? This is a paper published in 2015 in KDD. So this is where KDD is. This is like 2-dimensional space, right? So it has 5 authors. You can see the last author, which is Professor Yuri Leskovich, plays the most significant role because the length is the biggest, right? And among all the keywords, the keyword social media is the biggest for this paper. And eventually it got into the tube area of the key KDD. So that's why it's accepted, and it's even beyond KDD. So the gamma should be more than 1. And also another paper is this NIPS paper. So you can see the trend, okay? Then that's the conclusion of these 2 works, right? One, say, how can we use representation learning to learn for behavior modeling, right? To learn from multimodal data. Then the question down here at the last of this, at the end of this talk is, say, can we model the modal interactions using the interactive hierarchical attention like we showed in the first work, and the complementary using the tube simultaneously, right? So because they are both important the interactions among the modalities and the complementary among the items or among the modality is very important. So one idea is we can still use the IHA at the bottom. We have the multimodal encoders at the very bottom, and then go through the local attention and come to the interactive hierarchical attentions. And then at the end of the framework, instead of just a classification on the intention, we can replace with a complementary learning. Complementary learning to learn the complementary among the multimodalities. So okay, that's all for today's this part of the tutorial. So any question? Thank you.
Good afternoon, everyone. This is Yanfang. You can also call me Fanny. I'm now an associate professor in the Department of Computer and Data Sciences at Case Western Reserve University. It's my great pleasure to work with Nitesh, Meng, Chuxu, and Xiangliang for this tutorial at KDD 2020. Today, I'm going to talk about heterogeneous graph representation learning and its applications in cybersecurity and health intelligence. I'm going to first give the introduction and overview. As heterogeneous graph is capable of composing different types of entities and relations, it has been widely used in bibliographic network and social network. And we may ask, like, besides these two kind of widely applied fields, what are the typical research challenges for heterogeneous graph representation learning? And then beyond these two fields or some other widely applied domains, is there any other applications we can leverage this kind of techniques to resolve the problem that generate high impact? So to answer the above two questions, I'm going to talk about the research challenges and how we resolve the problem for heterogeneous graph learning, and then how we apply them for malware detection as well as other security applications. As more and more mobile devices connected to the internet, it has been infiltrates our everyday life and work, especially with the COVID-19 pandemic. More and more social activities has moved online, and Android operating system, which has been dominating the market with like over 87% market share, then its security is more important than ever, especially like now with like 194 billion mobile apps were downloaded last year. So like we usually can download the legitimate apps from official marketplace such as Google Play, but sometimes like we may download the unwanted apps or malicious apps from like the third market, and those malware sought for malicious software actually is designed to disrupt the mobile operations without the owner's informed consent. They may steal users' credentials and asset without informing the users, and they also may like send a text message, push advertisement, or like download unwanted apps without users' informed consent. And it's reported that over 1.89 million new Android malware infected more than 38 million mobile devices in the first half of 2019. So if like a user was in the mobile devices is infected by a ransomware, then this type of malicious software could block access to the victim's data or threatens to publish or delete it until a ransom is paid. So this kind of malicious software attacks pose like significant challenges to the users in cyberspace. So in this way, we have a series of work like resolving like heterogeneous graph representation learning problems, and then successfully applying them for intelligent malware detection. And this is several typical works like in terms of this research. So I'm going to first introduce like the first work using heterogeneous graph or named Heterogeneous Information Network for malware detection. This work has been published in KDD 2017, and it also won the Best Paper Award and Best Student Paper Award in the Applied Data Science Check. So I'm going to first introduce the system architecture. For all the collected Android apps, we will first analyze this app, and then we are going to convert the Android app into the small code and further analyze the converted code to extract the features, many including API calls. And because API calls can use to represent the behaviors of a segment of the code. And beyond API call extraction, we also further analyze the different kind of relationships among them. For example, we also analyze whether two API calls belong to the same code block, or they belong to the same package, or whether they are invoked using the same method. So in this way, this is able to depict more complex relationship between all these extracted API calls, which make the evasion even more difficult. And based on the extracted features, we construct the heterogeneous information network for representation. And then we propose the multi-kernel learning algorithms to build the classification model for malware detection. Means based on the training model for any given unknown apps, we are going to use the trained model to predict whether it belongs to benign fire or malicious app. So for the extracted features for each app, we extract the API calls from the converted small code, and then we analyze whether two API calls are within the same code block, or with the same package name, or using the same invoke method. In this way, to depict the relatedness over two apps, we further use the metapath concept to mirror the relatedness over apps. For example, these two apps are correlated if they include the same kind of API, and these two apps are related if their extracted API calls belong to the same code block. And in this way, we can further formulate the relatedness over apps. And based on that, we propose multi-kernel learning algorithm to build the classification model. And for any given unknown apps, after the feature extraction, we can use the device learning model to predict whether this given app is benign or malicious. So we collect the real-world data from Komodo Cloud Security Center, which contains two subsets of the samples, and then we perform the evaluations based on the precision, recall, accuracy, and F1 merits. And in the first set of the experiment, we evaluate the performance of different metapaths, and we can see that different metapaths they perform differently in Android malware detection, and compare with individual or single metapaths. The combined metapaths did perform better than the individual metapaths. So for the comparison, we also use the combined kernel using rate each metapath using its blessing score. And then we also perform the evaluation by comparisons with our proposed multi-kernel learning algorithms with the combined kernel, which are supervised versus unsupervised learning mechanisms. And from the result, we can see the proposed multi-kernel learning outperform the corresponding combined kernel mechanisms. And we also compare Hindjoy with other alternative detection methods, traditional machine learning methods, and then we can see because of more expressive representation using structured heterogeneous information network, Hindjoy outperform other kind of traditional machine learning methods in Android malware detection. And we also compare Hindjoy with other commercial security products. The experiment shows that it achieves better detection effectiveness and efficiency. The major reason lies in its novel higher level semantic feature representation and also the multi-kernel learning based on the constructed heterogeneous information network in feature engineering. And we also evaluate like the developed system in large-scale data set, and the result also shows that it's robust and also scalable for large-scale enduring malware detection. And this system has been deployed in real-world application. It has been incorporated into the scanning tool of Komodo mobile security product that protect millions of users in the cyberspace globally. So in summary, the major contribution of this work, this is the first work that heterogeneous information network has been successfully applied in the cybersecurity domain, and we propose novel structured feature representation to depict the Android apps for Android malware detection, which is more difficult and costly to be evaded. And then we also propose like multi-kernel learning algorithms for heterogeneous information network, which can learn from data to determine the importance of different meta paths, and thus perform better classification results in this problem. And it has been also successfully incorporated into the scanning tool for Komodo mobile security product, and which demonstrates like which demonstrates it's applicable in real world industry applications. Along this line of research, we further propose metagraph to vector to learn the node representation in the constructed heterogeneous graph or heterogeneous information network hint. Hint representation learning can be defined as, given a hint, the representation learning task is to learn a function that maps each node to a vector in a lower dimensional space that are capable to preserve the structure and semantic relation among them. So compared with metapath to vector, metagraph to vector is capable of depicting relatedness over nodes in the constructed hint by the derived metagraphs, and it also enables to fuse multiple derived metagraphs into a unified embedding. So if you are interested in the detailed work, you can refer the paper in KDD 2018. And then we further extend our work to resolve the problem of out-of-sample node representation learning in heterogeneous graph for real-time Android malware detection. Actually, like most of the existing works are based on static heterogeneous graph, which means like all nodes are known before learning, and then you need to obtain the representation for out-of-sample nodes to rerun the heterogeneous graph embedding and make the downstream classifier to retrain. And to resolve the real-time prediction problem, we need to tackle the challenges of out-of-sample node representation. So to resolve this problem, we propose a framework named AI Joy to learn out-of-sample node representation for real-time Android malware detection. The key idea is like we leverage the k-order neighbors of the in-sample nodes to represent any given out-of-sample node. So in this way, we don't need to rerun the embeddings, and then this also makes the downstream classifier feasible for classifying new arriving node without retraining. And if you are interested in this work for out-of-sample node representation learning in heterogeneous graph, you can refer to our paper in ICHKI 2019, AI Joy. And along this line of the research, especially tackle the challenge of adversary attack and defense on heterogeneous graph-based model for malware detection, we further extend our work. So basically for the adversary attack, which can be categorized into two types. One is poisoning attacks, which means like attackers can inject well-crafted poisoning nodes in the training data to make the classifying function. And the other category is evasion attack, which means like attackers can manipulate malicious samples at test time and to have them misclassified as benign without having influence on the training data. So actually, if like we will consider attackers' capability and knowledge, then it can perform the poisoning attack and also evasion attack concurrently. So to combat the evolving and joint malware attacks, systems such as HinJoy or AIJoy have demonstrated the success of heterogeneous graph-based model in malware detection. However, their success may also incentivize attackers to defeat heterogeneous graph-based model to bypass the detection. And by then, there had not worked on practical adversary attack or defense on heterogeneous graph data. So we aim to bridge this gap through the application in malware detection. The key idea for this work is like a fully device attack. That means we would like to simulate how attackers can leverage their current capabilities and also available knowledge to inject the target node, means like a newly released malware, by along with the poisoning node. They are going to concurrently to poison the data, the heterogeneous graph data, by injecting the poisoning node to protect the target node to evade the detection. And then for defense side, we aim to, in this like adversary game, for the defense, we aim to uncover the injected poisoning nodes in the heterogeneous graph to finally detect the target node. It's like the new malware. So the detailed work can be referred to our published paper in CIKM 2019 through like Alpha Cyber of our work. And I would like to also briefly elaborate like other applications in cybersecurity domains which can use or utilize heterogeneous graphs as well as the representation learning models. So we also expand and then propose like corresponding algorithms to resolve the representation learning problem in the security domains to tackle the problems for drug trafficker identification in darknet markets, and also used to enhance the social coding security in modern software programming cyber infrastructures, including GitHub and Stack Overflow. At the same time, we also extend this 9 works for key player identification in underground forums. So if you are interested in our work, you can refer to our papers in www. CIKM 2019. Besides the applications in cybersecurity domains, we also further investigate how attributed heterogeneous graphs and its representation learning can be leveraged for COVID-19 relief. So with the support from our NSF RAPID program, we have developed and launched an AI-driven system for dynamic COVID-19 risk assessment in the United States. As the novel coronavirus and its deadly outbreak have posed ground challenge to human society, to combat the global pandemic, one of the key is community mitigation. Before, according to CDC, before a vaccine or drug become available, community mitigation would be one of the most readily and applicable solution to slow down the spread of the virus. This is one of the examples of coronavirus outbreak in King County at Washington State. So a growing number of areas reporting local sub-national community transmission would represent significant trend for the worse in the battle against the novel coronavirus, which points to an urgent need for expanding surveillance so that we can better understand the spread of COVID-19 and thus provide actionable information for community mitigation. To achieve this goal, we may ask, although like during the quarantine or lockdown period, then we still need to go to the pharmacy or grocery store for essential daily life, or you may want to see the doctor if it's necessary. So in this way, if you would like to go for grocery shopping, which store should I go? Then which place would be more risky, while vice versa, and vice versa. So motivated by this problem, we propose an AI-driven system for dynamic COVID-19 risk assessment. The key idea is like we would like to leverage the large scale and near real-time generated data from multiple sources, including disease-related data, such as the numbers of COVID-19 cases, the number of deaths, the fatality rate, the new cases number, the new deaths, and also the demographic data, such as the population density, the distribution of age, income, education in a given area, and so on. And we also would like to consider the mobility data in terms of how busy a given area it is, and also like the social media data. We would like to analyze the public perception towards the COVID-19 pandemic. So based on this collected data, we devised an AI-driven model, which mainly leverage like integrates the conditional gain generative diversity network with heterogeneous graph for modeling to provide dynamic COVID-19 risk assessment in the United States. So more specifically, given the location, either user input or automatically positioning by Google Maps, the system will automatically provide risk indices associated with it in a hierarchical manner to enable people to select appropriate actions for protection while minimizing disruption to daily life to the extent possible. So this is the system architecture. Based on our collected data from multiple sources, we devised the system, including 3 components. We first construct the attributed heterogeneous information network to depict the relations among different hierarchies, like a given POI, the county, the state, and also the country. And then to obtain the public perception towards COVID-19 for a given area, to tackle the challenges that for a certain area, maybe there's not sufficient data to assess the public perceptions towards COVID-19 based on the collected social media data. We devised the conditional gain to generate the synthetic data vectors to obtain or to estimate the public perception in this area. And in this way, the perception of users can provide a complementary knowledge for us to estimate the risk of COVID-19 related to this area. And then by like enriching the constructed attributed heterogeneous information network to leverage both like vertical and horizontal information. Vertical means like we not only consider the given area, but also its affiliated county and state, like the related data. And horizontal means like we not only consider individual area, but also its neighborhood informations to comprehensively estimate the COVID-19 risk. So we devised like a novel heterogeneous autoencoder for the risk estimation. And in this way, the risk will be provided, the risk index will be provided in a hierarchical manner for any given area and its associated county and state. This could enable people to select appropriate actions. So this is our developed system. You can access our developed system through the website. The address is provided here. And in this way, it will automatically provide the risk index for your current location, along with like the risk percentile in your county. That means the percentile in your county among all the counties in your state, as well as the risk percentile of the associated states among all the states in the country. And for this dynamic map, you can also correlate any point of interest for the risk index And I'm going to show like a brief demo of this web system here. Again, you can access our web applications through this website here. The address is provided here. When you access our web application, you can obtain a dynamic COVID-19 risk assessment for any given POI, point of interest, through the dynamic map. For example, this is like the risk index in my current location. And in this way, you can see like the provided risk index. The higher number, the higher risk. And then it also provided the demographic density in terms of the population density in per square kilometers, in the associated counties, as well as the traffic status range from 1 star to 5 star. The large value, the more traffic, as well as the POI type. We also enable users to provide their perceptions in terms of the risk of their query POI. And at the right part, you will also provide the risk indices with the associated county and state. This is the risk percentile for Cuyahoga County. Among all the counties in Ohio State, this is the risk percentile of Ohio State across all the states in the United States. And again, to fulfill the initial intention. So if you would like to go to any grocery store, you can just like search in the text bar, grocery store. And then the system will provide the associated grocery store nearby grocery stores by provided rank from low to high. And then you can see like this is like because it currently is extremely busy. That means the traffic status is very high, and this is the corresponding risk index of this given POI. And then we can also compare different. This is not only the regional map, but also the national map. So we can do some comparisons. For example, let's check in New York. Let's say grocery store, Manhattan. And then we can see here in terms of like the comparisons in different city and different states. And this is like a grocery store in Manhattan. And then when you click like either you can click like any POI for your interest, and then you can see like a corresponding risk index associated with this POI in hierarchical manner. This is the New York City and New York State. So we can also compare other this is quite and New York City is like one of the most severe city across the country. And then let's see like how about Florida, Miami. And it's quite broad. Then let's narrow down. Let's see like a beach. And we can see like the corresponding risk index in Miami Beach. And then we can see that today, that means like July 31st, like Florida is in the highest risk across all the states in the country. And this provides like some actionable information for users for community mitigation. And we can also do comparisons with like lower risk areas, such as like West Virginia University in West Virginia State. And we can see here let's see what, okay, here is a grocery store, and then we can see like the risk is much lower than on the state of Ohio, Florida, and New York. So this provides a dynamic map for users, and we also provide the analysis board. So through the analysis board, we can see like the comparisons for different states in terms of the risk assessment, and as well as like the traffic transmission. We also estimate. We so often like the top traffic from out of state to the particular state. And then we also provided detailed information for the risk index for state level or like a county level. You can query for any of your interest, as well as like the case index growth rates, the case numbers, and you can also do the comparison of the state or counties for the new case trend analysis. Let's say here, we can compare like the new case trends, and then this would also provide like more detailed information for decision making for any organization or community leaders or policy makers. And we also provided the detailed information in the current date for all the states. So basically, this is like a debate system using AI-driven techniques, especially leverage the heterogeneous graph and its representation learning methods. Our system and generated data set have been made public accessible through our website, and our work has been accepted for publications. For detailed information of our work and then the device method can be accessed through our publication in JPHI and also CIK paper this year. And in the future work, we plan to expand the data collection and extend our models to improve its performance for risk estimation. We will continue releasing our dataset and system updates to facilitate researchers and practitioners to combat COVID-19 together. And after we launched the system for public test, the system named Alpha Satellite has attracted positive media and public attention from multiple channels. And it also recently received the Metro Lab Innovation of the Month for May 2020. And by far, it has had over 78,000 users as of July 30, which indicates the high demand from the public for effective computational tools to assist people with actionable information for protection while minimizing disruption to daily life. The system has receiving a lot of good feedback from the users on the ease of use as well as the utility of the relative risk estimation. And we would like to particularly thank the strong support from NSF and also DOJ and IJ. And my motto is innovation, research, education for a better world. I and my lab enjoy finding novel yet deep and elegant solutions to real-world problems that generate high impact. So I'm currently looking for multiple PhD students and postdocs doing supervised research or independent study with me at Case Western Reserve University. So if you are interested in the PhD or postdoc positions related to the area of data mining machine learning with the applications in cybersecurity and health intelligence, please feel free to contact me and send me email. Thank you very much. And now we are going to open for the discussion and Q&A.
Hello everyone, this is Chuxu. I'm an assistant professor of computer science at Brandeis University. In this part, I'm going to talk about task-guided relation learning in heterogeneous graphs. Many real-world complex systems can be modeled as a heterogeneous graph. For example, in e-commerce platform, different type of node, user, item, category are connected by different type of relations, such as buying, co-purchasing. In the web academic system, different type of node, organization, also paper and value are connected by different type of relation, such as paper writing, citing, In addition, the IT system can be also modeled as a heterogeneous graph, representing different devices connected by different type of relations. The chemical molecules is also a heterogeneous graph, representing different type of atoms connected by different type of bonds. The task-guided relation learning problems in the heterogeneous graph is to infer relations between any pair of nodes in the graph. There are many applications of relation learning in heterogeneous graph. For example, in e-commerce platform, recommending specific items to the target user. In the social media systems, predicting the followers of specific users. And also in the web academic system, recommending papers to researchers or help search reviewers for anonymous papers. Here we focus on the relation learning in the web academic system. Specifically, I'm going to introduce 3 recent work about task-guided relation learning in the academic graph. All of these 3 works study the same also identification problem and have very similar ideas. However, they have different model design and achieve the different performance. Okay, let me introduce the first work, task-guided and path-augmented heterogeneous network embedding for also identification. Given historical academic publication data, the problem is to develop a machine learning model to predict the potential authors of each new anonymous papers. The solution of this problem can be applied to different applications, such as paper recommendations or reviewer searchings. In the academic publication data, each paper is associated with different type of context informations, including also keyword year values. Then we can utilize this context information to formulate the paper embedding. Here, VP denote the paper embedding. We can see that it's computed by the weighted combination of different context information. Here, for example, we can pre-train the embedding of different context information such as keyword, reference, values, then do the weighted combination of all of these context information to get the final paper embedding. In addition, a latent feature is used to denote each also embeddings. The relevance group between each paper and each author is computed as the inner product of embeddings between author and the papers. Then we can utilize the pairwise ranking loss to formulate such direct relation between author and the papers. The previous step capture and model the direct relation between paper and authors. However, there are also many indirect relation between author and papers that can be extracted from the academic graph. The academic graph is represented as a heterogeneous graph consisting of different type of nodes such as author, paper, and values, connected by different type of relations such as also write paper, paper, publish it in value, or paper, cite papers. We can introduce the mental bus to capture indirect relations between different author and paper in the academic heterogeneous graph. For example, the APA mental path is able to capture the indirect relation between author and their collaborators' paper. The AP-VPA mental path is able to capture the indirect relation between author and the paper published in the same venues. Then the skip-gram model is utilized to model such indirect relations, which is to maximize the likelihood of context neighbor of each target node in different mental paths. By using some optimization strategy, the loss function is degenerated to the close entropy loss, between any pair of nodes in the heterogeneous graphs. So this idea is inspired by the network embedding model. After that, we can perform the joint optimization between task-guided pair-wise ranking and the network embedding. So this is the formulation of the final objective function. The first component is the pair-wise ranking loss between paper and authors. And the second part is the network embedding loss. The third part is the regularization term. So this page shows some experimental results using a minor academic publication data. We can find that the proposed model is much better than the feature engineering model. In addition, the proposed combined model of task-guided ranking and network embedding is better than the task-guided ranking model or network embedding model. It demonstrates that both pair-wise ranking component and network embedding component in the joint objective function will make effect in improving the model performance. So and the second table here shows two case studies. We can find that the proposed combined model can correctly predict some authors of the anonymous papers. Well, the previous model used various context information of paper and developed a shallow network embedding model to solve the problem. There's a following work called Camel, which only utilizes paper text information and develop a deep learning model to further improve the performance. Now let me introduce this work, content-aware and mental path augmented matrix learning for author identification. Similar to the previous work, Camel also consider both direct relation and indirect relation between paper and authors. Here we can find the direct relation between paper and author is formulated as distance matrix ranking loss, and different mental paths are utilized to extract the indirect relation between paper and authors under different semantic context. Then the skipgram model is utilized to model those indirect relation between paper and authors. The major difference between Camel and the previous model is that Camel only utilized the paper text information and develop a deep learning model to encode the paper information. So from this figure, we can find that the paper embedding is formulated by the deep language model, which use the pre-trained word embedding and the recurrent neural network to represent each paper embeddings. Then we can perform the joint optimization between the direct relation modeling and the indirect relation modeling. And also the joint objective function is able to capture the paper text information using the deep content encoders. This page shows the experimental result using the A minor data set. So we can find that Camel can outperform the previous heterogeneous network embedding model. The average improvement is around 9%. So the previous two models solved the problem by learning also and the paper embedding independently. There's another framework that's trying to learn the author and paper relation pair embedding directly and further improve the performance. Now let me introduce this framework, task-guided pair embedding in heterogeneous network. This model included two major parts, the pair prediction part and the context prediction part. So in this figure, the left part is the pair prediction part, and the right part is the context prediction part. So in the pair prediction part, after getting the paper embedding and also embeddings, we can formulate the also and the paper relation pair embedding by using the combination of also embedding and the paper embedding. Here, GUV denote the relation pair embedding, and it's formulated by the combination of the two embeddings. Then the closed entropy loss can be utilized to formulate whether each relation pair is true or false. As for the context prediction part, different mental paths between the target paper and the target also are extracted. Then the recurrent neural network is utilized to encode the context neighbor sequence in different mental paths. So here, FCV denote the encoded context neighbor sequential embeddings, and GUV denote the relation pair embeddings. Then the context prediction loss between relation pair embedding and context neighbor embedding is utilized. Finally, the model performed the joint optimization between pair prediction and context predictions. This table shows the experimental result on the same A minor data. So we can find that the proposed model, TAPR, is better than the previous heterogeneous network embedding model and the CAMELS models. Well, to summarize, the first model, heterogeneous network embedding model, use various paper context information and develop a shallow machine learning model of pairwise ranking and heterogeneous network embedding. And the second model, CAMEL, only use paper text information and develop a deep learning model of context encoder, pairwise ranking, and heterogeneous network embedding. And the last model try to then denote the pair relation pair embedding directly and perform the joint optimization of pair prediction and context predictions. That's all about the task-guided relation learning in the heterogeneous graph. If you have any question, please let us know. Thank you. So, hello everyone, this is Chuxu, one of the organizer of this tutorial. So we are going to have a 20-minute break till 3 p.m. So welcome back at 3 p.m. Hello everyone, welcome back to our tutorial. For the second part, we are going to talk about attributed network embedding, knowledge graph alignment, heterogeneous network embedding, and the graph neural network. So let's continue our tutorial.
Hello everyone, I'm Xiangliang Zhang. Thank you for your interest in this tutorial of semi-supervised attributed network embedding. First, let me give a summary of the study in this topic. In the beginning of 2000, semi-supervised node classification problem was studied as the graph Laplacian regularization problem. The most popular method is label propagation. I will introduce it later. In 2014, when deep work was proposed, it was for unsupervised node embedding based on the skip graph model. After that, a number of approaches have been studied for semi-supervised node embedding. I will talk about planetoid in this tutorial. Very soon later, graph neural networks were proposed for learning the attributed network embedding. I select several representative ones. I will share with you them in this tutorial. So this is the outline of this tutorial. I will first give a brief introduction, and then I talk about 3 types of approaches, and then I will give some discussions. Attributed network can be found in many applications. For example, citation networks, co-author networks. It's different from planar network because the nodes in attributed networks have node features. We can represent an attributed network by the network topology matrix and node feature matrix. So the embedding is to learn new representations for nodes in a lower dimensional space, which is lower than the original node feature space. And then the embeddings can be used for node classification, profiling, link prediction, commit detection, and many others. Semi-supervised attributed network embedding introduced labels in the embedding process. As we can see in this graph, we have 2 nodes with labels in the red class and in green class. And our target is to predict the labels for the other unlabeled nodes. That is saying, we have the attributed graph represented as network topology matrix A, node feature X, and the label vector Y. We will learn node embeddings for the nodes with the help of the Y. And the learned embedding X will be used for doing classification to infer the labels for the unlabeled nodes. And because Y was used in the node embedding process, we expect that the learned X can do prediction more accurately than the X learned in an unsupervised way. We will talk about first the solution in the category of label propagation. And actually, label propagation is different from the other 2 types of solution when solving this semi-supervised node classification problem, because it directly uses A, X, and Y to do the prediction of Y for the unlabeled nodes. It doesn't learn this node embedding. But in the other 2 types of approaches we will talk about later, they infer the embedding X and then they do the classification. So by the name of label propagation, we can say it works by propagating the labels from the labeled nodes to the unlabeled nodes. And in order to propagate the labels, random walks were conducted on the graph. We show one example. Say, from the unlabeled node, node 9, we can take a random walk to node 7. And from node 7, we can go to a labeled node here. Once we arrive at this labeled node, we will stay with it. We will not go to any other place. Or in other words, this labeled node is an observing node. But of course, we can first go to 7 and then we can go to 5, and then we can go to this labeled node again, and we will stay there. So the prediction for the labels is made by this equation. We can say the probability for predicting the label in right for one node is calculated by the probability for the nodes it visited in the random walk process being with class right, and also the transition probability between the two nodes I and J. So the transition probability is actually defined by the weights on the edges. So we can say if there is a high probability moving from node I to node J, and then the label of this node J will contribute more in the prediction of the label I. If we define a label vector Y, which is composed of the known labels and the unknown labels given as 0, we can multiply this Y multiple times with the transition probability P. We can infer the labels for the unlabeled nodes. This transition probability is defined in this way. As we know, the labeled nodes will stay with themselves, will not go to any other nodes. Then the top part of this transition probability matrix P is made of this identity matrix and 0. And the second part of this transition probability matrix P is calculated based on the edge weight. You can see there is no embedding learned in this process, and the label propagation algorithm can be implemented in an iterative way as given here. Label propagation is considered to be equivalent to the minimization of a semi-supervised loss function derived from the graph. The loss function is composed of several parts. The first part calculates the difference between the ground truth label and the predicted label. And as we can see, this is a supervised loss because it falls. The predicted label should be close to the ground truth label. And the second part is actually considered as an unsupervised loss because it mirrors the consistency between the predicted label and the geometry of the graph. So the definition is given here. So Yi is the label predicted for node I, and Yj is a label predicted for node J. So if the node I and the node J has a higher weight, we expect that the predicted label for node I and node J should be the same. Otherwise, it should be different. And the last term is actually a regularization term. And the second term is also somehow considered as a Laplacian regularization because it's based on the graph Laplacian matrix, which is D minus W given here. So later we will discuss some other methods, and the loss function will be formulated in a very similar way like what we discussed here, composed of supervised and unsupervised loss. So let's move to the second type of approach. It's based on skip-gram model for learning the node embeddings. So first, let's see the deep work using skip-gram model for learning node embedding in an unsupervised way. And here, node features are not considered. It works for the planned network. So given a graph, we can conduct random walks on the graph. And the random walk will give us sequences about the nodes visited. And we can see here for node 1, V1, we have neighbors visited before and after it. And these nodes are considered as neighbors, for example, in a social graph, these are the friends of V1. And we call these neighbors as the contacts of V1. So the idea is we want to learn embeddings for node V1 in order to predict the context correctly. So you can see the object function here is defined to predict the context of a node given the embedding of the node. So if we can predict the context correctly, then it means the embedding vectors we learned are correct. So we know this is learned in an unsupervised way without considering the labels for the nodes. So the learned embeddings can be used for any purpose, for classification, clustering, commit detection, and many others, link prediction. In order to work for the semi-supervised attributed network embedding, we have to introduce a loss function. And this loss function, like what we introduced in the label propagation method, is composed of supervised loss and unsupervised loss. In the method of planetoid, the supervised loss is defined to predict the label correctly for the labeled nodes. And the prediction is actually made by the embedding of the feature and the embedding of the nodes based on the network topology. So as you can see here, the target is to learn the feature embedding, the node embedding, in order to do the prediction yi correctly. And the unsupervised loss here is defined to predict the context. This is similar to what was used in the object function of deep work. We try to predict the context, try to predict the neighbors. And the context here is defined in two ways. First, the context can be defined based on the network topology of this adjacent matrix A. That is saying we have the positive context C within a few hops of node I, and for the negative context, it can be far away from the node I. This is consistent with what was used in the deep work formulation. The second type of context is defined based on the labels, since we have a few nodes with labels available. The positive context is defined as those with the same label as the node I. And for the context with different labels from node I, these are the negative contexts. So overall, we try to solve this embedding problem by doing the prediction of the label correctly and doing the prediction of context also correctly. Then as you can see, the learned embeddings will be used for doing the prediction for the labels for those unlabeled nodes. Next, let's talk about approaches by using the graph neural networks. We first briefly talk about the graph neural networks presented in GCN and graph stage. The idea here is to aggregate the neighboring nodes to get the embedding vector for the target node. For example, we can sample 3 first-order neighbors and 5 second-order neighbors here. Then 2 aggregators are applied to aggregate the vectors in the neighborhood. And these aggregation functions can be simply by taking the average of all the vectors in the neighbors. Or we can use LSTM, or can just by doing pooling to get the aggregation vector. And these aggregation vectors will be the embeddings for the target node here. And then the embedding vector can be used for different purposes. In order to learn the weights in the aggregation function, we can define different type of loss functions. We can use the semi-supervised or supervised loss function here by making the prediction correctly based on the embedding vector. We can also do the prediction about the context. And the idea is similar to what we used in the deep work model. So actually, the graph sage or the GCN, they try to sample the neighbors and then take aggregation of the neighboring nodes. But in this sampling process, we may not consider all the useful neighbors. So in another recent work called Graph Attention Network, GAT, attention was used to have a better aggregation of the neighboring nodes. But there are other solutions. For example, in a recent work, there is an attributed random walk introduced to have a better aggregation of the neighbors. So the idea here is, given an attributed network, for example, it is a citation network, and we have the vectors here for the nodes. And these are the feature vectors. For example, the words appeared in the papers in the citation network. And we can first construct a biparty graph by linking the nodes with the words appeared in the paper. For example, node 1 has 3 features, 3 words, delta 1, delta 2, and delta 3. They are linked here. But of course, we can preserve the original graph structure. So then the attributed random walks was conducted by either working on the biparty graph or working on the original graph. Then by doing these two kind of attributed random walks, we can have the random walk sequence. And then these random walk sequences are given to a graph recurrent neural networks. And these graph neural networks will learn the embeddings for the nodes and also for the attributes. Then polling is used to get the final representation for the node. There are other ways to conduct the attributed random walks. Similarly, we can transform an attributed network to a heterogeneous network by preserving the target nodes and creating the bridging nodes. And these bridging nodes are connected to the target nodes if the feature appeared in the nodes. And we can conduct random walks on this heterogeneous network by considering 3 different cases. And we can consider the move was from a target node to another target node, or it was moved from a target node to a bridge node, or it was moved from a bridge node to a target node. And some parameters P and Q and R are defined here, like what was done in the Notre to consider how to search in a graph for the neighbors. So all of the previous attributed random walk considered the walking from nodes to the attributes. Or in the deep work on Notre, the walking was conducted without a clear purpose. In this case, the embedding vectors learned can be for universal purpose. And if we want to introduce some bias random walk, it depends on some hyperparameters that should be tuned. So next, I'm going to introduce another work that consider the node classification as a game. And the random walk is for working with a goal to win the node classification game. Agent here is a student. And the student wants to classify a paper assigned, for example, by a professor. And the student is new in the field. And the student can read a set of papers to help the classification task. And the state of a student is the current reading papers, and of course, with accumulation of the knowledge by reading all the selected paper previously. And the action here is to choose another paper to read. And the reward can be the correct classification of the paper. So if we demonstrate this game on a citation graph, we have the paper that's in black here assigned to the student to classify. And the student has to take action by reading some papers following the citation links. And then the student can accumulate the knowledge by reading more and more papers, more and more relevant papers. And when the student read enough, then the paper here can be classified accurately. So then the key idea here is how to select the papers to read. And then once selected the papers, how to accumulate the knowledge in the papers. In the recent work, there is a recurrent network designed to solve this problem. So in this recurrent network, there are several building blocks. There is one network, here is called the score network, to decide which papers to read, or in other words, where to go on the citation graph. It will take the current node, contents, and the neighboring nodes, and then select one paper to read or an action. And then once the paper is selected, a history network here is used to memorize what has been read. And then this updated memory and the selected action will be sent to the next step for deciding the next paper to read and for refreshing the memory. And after a number of steps, the learned embedding vector is used to do the classification. And the agent will earn a reward, for example, 1, if the classification is correct. Otherwise, it will receive a penalty -1. So as you can see, this is not a random walk. This is a precise. In order to win the game, the agent decides where to go. This method is compiled with several state-of-the-art solutions, for example, the GraphSage and Planetoid. So the results show that this method has better performance than the other baselines. It's because the working here is not in a random way. It is based on the target to classify the nodes correctly. And based on reinforcement strategy, the agents know where to go. However, the agent cannot decide when to stop. There is an analysis about how the walk length can affect the accuracy and the running time. So we can see with more steps, we can have better and better accuracy, but accuracy cannot grow too much after 10 steps. That is saying the agent may have to stop without going further. There are several interesting open issues in this topic. First, if we can have transferable knowledge among multiple graphs. For example, in molecule graph and some other graph in special domains, we may want to learn the transferable knowledge in order to do better prediction about their property or about some links. And the second issue is this heterophily, incompleteness, and noise in the graph. So we know that in some graphs, the labels may not smooth among the neighbors. For example, in a social dating network, males are more likely connected with females, and if we do gender classification, we may not have this label smoothness in the neighborhood. And we may have missing links, and we may have noisy links in the graph. If we rely on only the classification labels to do the graph embedding, we may not have the features learned correctly for the nodes. And it will be interesting to have self-supervised learning for the graphs. We can introduce some other weak signals, weak supervising to learn the graph embeddings. And of course, the current solutions may work or may not work for large-scale graphs. We need effort to make efficient approaches for the large graphs. So the last issue is there are many graphs, social graphs, citation graph, and knowledge graphs, and they may have dynamic features. And how to conduct continual learning with this dynamic graph is also an interesting question. So here are the references I mentioned in this tutorial. So if you are interested, you can read more details in these papers. And in the end, I want to send my acknowledgement to my students, visiting student collaborators who contributed to the study in this topic in my group. If you have any questions, you can send me an email to ask.
Hello, everyone. Do you have any questions about this part, attributed network embedding? If no, then we continue the tutorial.
Hello, everyone. I'm Xiangliang Zhang. Thank you for your interest in this tutorial of semi-supervised graph alignment. Graph alignment is to find the node correspondence across different graphs. For example, given a knowledge graph with entity words in English and the other knowledge graph with entity words in French, graph alignment is to find the entity words that have the same semantic meanings in these two different graphs. We can also do user alignment in social graphs, and the aligned users can be used for recommendation problems and also for user profiling. Knowledge graph alignment has been studied in different ways. The earliest study used crowdsourcing, handcraft features, or extra resources. Translation-based approaches mostly were studied in a supervised way. This tutorial will cover two recent approaches in a semi-supervised way. Graph neural network has also been very recently studied for doing the graph alignment. And this reference work will be provided in the end of this tutorial. Social network alignment was studied in another branch, and there were traditional methods based on matrix factorization and also recent approaches based on supervised embedding. We focus on the semi-supervised knowledge graph alignment in this tutorial. So the idea is we have the labeled pairs that can be used as a training site to align the remaining node pairs in different graphs. However, it's often expensive to have a large number of labeled node pairs. And also, the labeled node pairs may have noise that will generate the alignment results. So I will first introduce two approaches that leverage the large amount of unlabeled node pairs to boost the performance of graph alignment. These two approaches are based on cycled consistency and the optimal transport. The first approach based on cycled consistency is named SEA, semi-supervised entity alignment. Given two graphs, we can learn the embeddings for the entity words in these graphs. And these two embedding spaces are different. But the aligned entities should have the close embedding vectors if they are mapped to the same space. Therefore, we can use transition matrix M1 to map the entity embedding in graph 1 to the graph 2 embedding space. And then we can compare if the mapped entity is close to the corresponding entity in graph 2. And the supervised loss here is defined to mirror the difference. In a similar way, we can map the entity words in graph 2 by transition matrix M2 to the graph 1 embedding space. And then we can also compare if the mapped entity embedding is close to the corresponding entity in graph 1. So the loss here mirrors the difference. In addition to the supervised loss, we introduce a reconstruction loss. It is because after the entity of one graph mapped to the embedding space of the other graph, we can map them back. As we can see here, the embedding of an entity EI is mapped to the embedding of graph 2 space by M1. And it can be mapped back to the embedding space of graph 1 by M2. That is M2 multiply M1 and the embedding vector of entity EI. So then we can check the difference after mapped back. Then this distance should be small if M1 and M2 are well learned. So this reconstruction loss here is defined to mirror the difference. In a similar way, we can compare the entities in graph 2 mapped to graph 1 and then mapped back to the graph 2 space. And the reconstruction loss is calculated in a similar way. So this is how the cycled consistency is used to learn M1, M2, which are the transition matrix that can be used for the alignment of the other unlabeled nodes. However, we may have another limitation, that is we fear matching the whole distribution of the embedding vectors. For example, we have blue embedding vectors for the entities in one graph and the orange embedding vectors for the entities in the other graph. The labeled pairs should be close after mapping by the transition matrix. However, there are some nodes that should be aligned after the transition matrix mapping, but if without considering the whole distribution, we cannot align them correctly. So we will introduce the idea of optimal transport to minimize the alignment loss both in the entity level and the group level. So the method introduced here is named OT. The target is to minimize both entity level loss and the group level loss. The entity level loss is defined in the same way like what we had in the ICA model. The group level loss is defined as a difference between the entity distribution in one graph and the distribution of the mapped entity from the other graph. The difference is minimized by using a minimax function, which involves a discriminator that distinguishes the entities from two different graphs. The transition matrix M1 and M2 are optimized to fold the discriminator. Overall, M1 and M2 are optimized to minimize both loss functions. We compare the performance of the ICA model that considered the cycled consistency and the OT model that considered the distribution alignment with several baselines. And we can see here the ICA model had a better performance than all the baselines, and the OT model generally had a better performance than the ICA model. That is saying, considering the cycle consistency and also the distribution alignment are both very important. So next, we will talk about robust graph alignment. Semi-supervised graph alignment uses a small set of labeled node pairs as the training set. The noise in the training set will have negative impact on the model performance. As we can see in this example, because of the noisy link in black, we cannot have the expected alignment results. The embedding distribution was affected by the noisy link, and we cannot have correct the alignment for the node 4 and 5 in the two different graphs. So the idea is, how can we use unlabeled nodes to help the noisy detection and then build a robust alignment model? It is because, on the one hand, noisy detection can be helpful to provide reliable node pairs to have more accurate graph alignment. And on the other hand, a precise graph alignment model is very useful to identify the noisy pairs. The model to be presented here is called REA, the Robust Entity Alignment Model. To build a robust model, we assume that we have a small set of trusted aligned pairs in the training set. However, there exist other untrusted pairs in the training set. These untrusted pairs may be noisy pairs, may not be noisy pairs. So in our model, we will learn a discriminator trying to identify the noisy pairs and also the trusted pairs in the unlabeled set. The model has two parts. The first part is for noisy aware entity alignment. It is similar to the regular entity alignment by learning entity embeddings. However, we have a trust score here introduced to measure how much we can trust the training pairs. It is because the aligned site may have noisy pairs. This trust score is calculated based on the output of the discriminator. The discriminator here is learned in the second part for noisy detection. This part follows the framework of GAN. It tries to distinguish the trusted aligned pairs and the noise pairs. The discriminator learned here will be able to calculate a trust score for also the unlabeled pairs. And for those has a high trusted score, we can add them to the training site, and then we can learn better embeddings, and then can have better noisy discriminator. And we share some evaluation results here by comparing the robust entity alignment model with some other baselines. From the result, we can see the robust entity alignment model has better performance comparing to the baselines, and also it can correctly detect the noisy pairs in the training set. In the end, we share some discussions. In this tutorial, we introduced the two semi-supervised network alignment model based on cycled consistency and optimal transport. We show that both of them are helpful to improve the alignment performance. And also we show that unlabeled data can be used to build robust network alignment model. In this topic, there are some other interesting problems to study. For example, to detect the noise in the graphs and the links across graph jointly. We can also consider how to detect and how to protect the alignment model against adversary attacks. And we can also study the alignment of the dynamic graphs. So these are the references we mentioned in this tutorial. Thank you for your attention. And in the end, I want to thank my students, especially Zhang and Lu, who worked on the topic of graph alignment.
Everyone, any questions about noisy graph alignment part? Okay, let's go to the next part.
Hello everyone, this is Chuxu.
For this part, I'm going to talk about heterogeneous graph representation learning. Heterogeneous graph represent different type of nodes connected by different type of edges. In addition, the node and edge in the graph could be associated with different attribute or content features. Many real-world complex systems can be modeled as heterogeneous graph. For example, in e-commerce platform, different user item categories are connected by different type of relations. In the web academic system, different organization also paper value are connected by different type of relations. The IT system could also be modeled as heterogeneous graph, representing different devices connected by different relations. The chemical molecular is also a heterogeneous graph, denoting different type of atoms connected by different type of bonds. The proven definition of heterogeneous graph representation learning is given a heterogeneous graph, develop a machine learning model to learn vector representation for each node in the graph, so as to facilitate different downstream graph mining tasks. There are two main approaches. For heterogeneous graph representation learning. The first one is the network embedding approach. In each network embedding model, the node is denoted as an embedding vectors. Then we can employ proximity preserving methods, mainly the structure proximity, to optimize the embedding vector of each node in the graph. Then the optimized embedding vector could be applied to different graph mining tasks. The second one is the graph neural network model. In each graph neural network model, the node is associated with different attributed features. Then we can employ the message passing approach, which is to use a neural network to aggregate the feature information of each target node, to aggregate the neighborhood feature information of each target node, then the representation of each node. The parameter of the neural network could be optimized by using both supervised loss or unsupervised loss. Then the linear representation of each node could be applied to different graph mining tasks. There are so many heterogeneous graph representation learning models. For this part, I'm going to present 4 recent work about heterogeneous graph representation. The first one, mental path to vector, is representation learning for heterogeneous networks. The second one, Zhang, is representation learning for semantic associative heterogeneous network. The third one, Meng, is heterogeneous graph attention network model. And the last one, Jiang, is a heterogeneous graph neural network model. The first one and the second one are based on network embedding model, and the third one and last one are based on the graph neural network models. Now let me introduce the first work, mental path to vector. Mental path to vector is a quite popular model for heterogeneous network embedding. There are 2 major points on mental path to vector: mental path work and the heterogeneous skipgram. Different from homogeneous network embedding model like deep work and node to vector. Mental path to vector employ mental path work to capture the heterogeneous structure information in heterogeneous network. Then mental path to vector applies skipgram model and the heterogeneous skipgram model for context enabling modeling in the mental path work. This page shows the detailed model design of mental path to vector. Let's take the academic network as an examples. Academic network represent the different node organization, also paper value connected by different type of relations, such as also write paper, also collaborate, also paper side papers. Based on this heterogeneous network, we can extract different mental paths. For example, APA, which denote also paper also. APVPA, which denote also paper value paper also. Then we can use different mental paths to sample a set of node sequence in heterogeneous networks. After that, we can employ the skip-gram model to model the context information in different mental paths sequence, which is to maximize the context neighbor likelihood of each target node in different mental path sequence. Another major difference between mental path to vector and the traditional homogeneous network model is that when doing the negative sampling in the skip-gram model, the mental path to vector also consider node types. Here shows some sample result, experimental result of mental path to vector. The first table shows the experimental result for node classification. We can find that mental path to vector is better than the homogeneous network embedding model for node classification. The second table shows the experimental result of node clustering. It's easy to find that the mental path vector outperform the homogeneous network embedding model. The previous mental path to vector only consider heterogeneous structure informations. There is some following work which consider both heterogeneous structure information and the content information in the networks. Now let me introduce this following work, Zhang, representation only for semantic associated heterogeneous networks. The major motivation of Zhang is that there are many heterogeneous networks associated with test information. For example, in academic network, different also paper value are connected by different type of relations. In addition, each paper node is also associated with text information such as abstract. And similar to the mental path to vector, Zhang use mental path work to capture the heterogeneous structure information in the heterogeneous network, then use heterogeneous skip-gram model to model such informations. In addition, Zhang also consider the text information in the heterogeneous network through a deep semantic encoding function. Then Zhang performed joint optimization of heterogeneous skip-gram model and the deep semantic encoding function. This page shows the detailed model design of Zhang. Let's take the academic network as the example again. So by using different mental path work, we can sample a set of node sequences in the academic network. For the nodes that are associated with text information, such as a paper node in the academic network, it's represented by two types of embeddings. The first one is a latent embedding. The second one is the semantic embeddings. The semantic embedding of each is encoded by the deep semantic encoder function, which is actually a deep language model. Here it's used the pre-trained word embedding and recurrent neural network model to get the final semantic embedding of each paper. After that, we can perform the joint optimization of deep semantic encoding function and the skip-gram models. In the objective function, this kind of semantic information is taken as a priori constraint on the objective function of skip-gram models. So by using some optimization strategies, the objective function is degenerated to the closed entropy loss with a regularization term. So we can find that here theta we denote the latent embedding, Fy we denote the semantic embedding of node B. So by using this objective function, we try to make the learned semantic embedding and the latent embedding of node be as close as possible. This page shows some experimental results of Shine. So the first table is the result of link prediction. The second one is the result of node classification, node recommendation. So we can find that the Shine can outperform both homogeneous network model and heterogeneous network embedding models for both link prediction and node recommendations. This picture shows embedding visualization of Shine. So the paper and also different 4 different areas, which is computer vision, human, HCI, data mining, and theories. So we can find that paper embedding also embedding of different labels are clearly separated, which demonstrate the good performance of Shine. Both of previous 2 model, mental bus 2 vector and Shine, network embedding model. There are also some graph neural network model for heterogeneous graph representation learning. Now let me introduce the first model, HAM, heterogeneous graph attention networks. The major idea of HAM is to perform the combination of node level and semantic level aggregation. This picture shows the main idea of HAM. So in the node level attentions, different mental paths are extracted from the heterogeneous network. Then it uses node level attention mechanism to aggregate the neighborhood feature information in each specific mental path. Then since different mental paths have different semantic meanings, it further introduces semantic attention to aggregate the information in different mental paths. This picture shows the detailed model design of HAM. So in the first step, node level aggregation. Here, HJ represent a context neighbor of node I in a specific mental path. Then we can use a multi-head attention mechanism to aggregate the context feature information in each specific mental path. In the second step, for semantic level aggregation, suppose there are P mental paths, and assume that each mental path should have different semantic meanings. So we should further introduce semantic level attention to aggregate the learned embedding in different mental paths and get the final embedding of each target node. This page, this table shows the experimental result of HAM for node classification task. So we can find that HAM is better than homogeneous network embedding model, heterogeneous network embedding model, and graph neural network models. The previous model, HAM, only considers structured informations for learning the node embedding in heterogeneous graph. There is also a following work which considers both heterogeneous structured information and heterogeneous content information. Now let me introduce the last work, Jiang, heterogeneous graph neural network. The motivation of Jiang is that the heterogeneous graph is not only associated with the heterogeneous structure information, but also associated with the heterogeneous content information. For example, type K node, the node of type K in this graph is associated with different type of heterogeneous content, such as attribute, text information, and image information. And we should develop a heterogeneous content aggregator to aggregate the content information in each node. This picture shows the overall framework of Jiang. So after sampling each type of context neighbor of a target node, the node A here, we can do the feature extraction and feature pre-training. Then we can utilize a heterogeneous content aggregator to get the content embedding of each type of node. After that, we use another type-based neighbor aggregator to get the embedding of each type of neighbors. Since each type of neighbors should have a different impact, we further introduce a type attention mechanism to aggregate the embedding of all type of neighbors and get the final target node embeddings. The general graph context laws can be utilized for model optimizations. This picture shows experimental results of Jiang in different tasks using different data sets. This is the result of link prediction. This is the result of node recommendation, and this is the result of node classification. So we can find that Jiang can outperform both heterogeneous network embedding model and the graph neural network model. And the last picture here shows the embedding visualization of node of different labels. So we can find that node embedding of different labels are clearly separated. Well, to summarize, the first work, mental path to vector, use mental path work to extract heterogeneous structure information, and then utilize heterogeneous scapegram model to learn the node embedding. And the second model consider both the heterogeneous structure information and content information in the heterogeneous networks. The third model perform both node level and semantic level aggregations to learn the node embedding. And the last model performed joint optimization of heterogeneous content aggregation and the heterogeneous neighbor aggregations. That's all about this part, heterogeneous graph representation learning. That means no, if you have any question.
Hello everyone, any question about this part, heterogeneous graph representation learning? If not, then let's go to the next part.
Thank you.
Hello, everybody. My name is Meng. I'm an assistant professor at the Department of Computer Science and Engineering at the University of Notre Dame. So I'll talk about graph neural nets for dynamic graphs and anomaly detection. So in this tutorial, I'll go through as many as 5 works in just around 30 minutes. So I'll just catch the main ideas of each work. So the first 4 works are mainly about how to apply graph neural nets on dynamic data, on temporal data. So the first one is called streaming graph neural nets in CGIR. The second one is evolving graph convolutional networks in AAAI, and then modeling the co-evolution of the attributes and the structures, and also use a calendar structure to model the time information. And last one is a new loss function for graph neural nets based anomaly detection. So firstly, in this streaming graph neural nets, they from the title you can understand that they try to process the streaming data. So every time we got a timestamp, and at a new timestamp we have a new link coming in, we call a new interaction. So suppose at a time t7 you got a new interaction v2 and v5, and they believe that this kind of new interaction depends on 2 parts. So that's why they design 2 components. One is called update component. So the update component means the very recent status of the nodes. Okay, so here the T7 is this new interaction is between V2 and V5. So what was the very recent update on V2? It's T3, right? You can see here they have T0 and T3. So the most recent is T3 from V7 to V2. And what's the most recent interaction on V5? So we have T6, T5 is T6, right? So it's a T6 from V5 to V3. So, so the idea is we should use a very recent updates on these two nodes to learn the new interaction, to predict new interaction. And the second part is called propagation component. That is, looking at the neighbors of this V2. So for the V2 is connected to V1 and V7, 1, 7, and the V5 is connected to V3 and 6, the 3 and 6. So the neighbors of this V2 and V5 have impact on the new interaction. So aggregating the information from neighbors, from V1, V7 to V2, and from V3, V6 to V5 is absolutely important. So you got this kind of update component and the propagation component. For each type of component, they have novel design. So here is their the procedure of this update component from finding the very recent status of the nodes in the new interaction, and then perform an update on there, and eventually concatenate down to making the prediction of the new interaction. Okay, so this is the operation on the update components. They design for each timestamp. They have this the merge unit, S update unit, and direct unit to process the updates. If you are interested in the detail of this operation, please go to read their paper in CGR 2020. And this is the update unit. The update unit is a component in this update component, right? As update unit. Okay. So then here is the propagation component. It's the second component, right? The first one is update component. Second is propagation component. So basically, it's retrieving the neighbors of the nodes in the new interaction. Okay, the neighbors of V2 and neighbors of V3 or V7, sorry, V5 actually, and all together to propagate the information onto the nodes and then making the prediction on the new interaction. So with this kind of novel framework, they perform experience, and one task is node classification. They compare with label propagation, graph sage, and graph convolutional neural nets, and a dynamic GNN. Okay, so then you can see here performance, and then things they name their work DYGN. That's quite interesting. It's not streaming GN, right? So then the second task is link prediction. Then you can see this DY or DGN performance based on this MR recall metrics, okay, on multiple data sets. The second work is evolving graph convolutional networks. So in this work, their idea is, for each timestamp, actually can perform a graph convolution network to process the data, to learn the node embedding, and to build, use recurrent neural nets to learn the sequential patterns in this time series, right? It's graph time series. It's evolving evolving graphs. Okay, so GCN and use RN to connect the GCNs. So they perform the proposed two kinds of algorithms. One is evolving graph convolution unit H, and the other is evolving graph convolutional unit O. Okay, given they define as GCN, and then perform weight evolution, and then use two kinds of units to perform this the learning. So for the H version, you can see they use a GRU to learn the impact of the weights in T-1 on T, okay, to learn that. While in the O version, they use LSTM to learn the dependency between the neighboring timestamps, t minus 1 t, and then perform it on the graph convolution network at time t. Okay, this is graph convolution network at time t. This is like the dependencies that learned from the RN model. So GRU and RSTM are two kinds of RN models. They perform on this in this framework. So based on different kinds of RN models, they have different version of the framework. Okay. So in their experience, they also perform on link prediction. Okay, on multiple kinds of data sets, quite a lot of data sets. Right. They show that this H version and O version, they perform pretty well compared to the existing methods. And they also show the performance on node classification and link classification. Okay, the third work is called modeling the attribute and structure coevolution. So the motivation is on a network, actually, you know, the impact of the attributes. You could see the impact of attributes on the structures, and you can also see the impact of structures on attributes. They mutually impact each other. For example, if you got attributes like the expertise of or the keywords in the publication of a researcher, it's like expertise of the expertise category of the researcher. Those kind of attributes may change your collaboration links. So suppose because you got a data mining topic, and you may collaborate with computer vision people because you all work on data, image data maybe, and you got this kind of collaboration. And then this collaboration link can further impact your decision on working with many other kinds of authors, because after you work with computer vision people, you got the computer vision knowledge, right? So you can further work with the robotics and the machine learning. So then build more links. You got new attributes and change the structure. So basically here, node attributes and graph structures are co-evolving. So if you look at the Pearson correlation between the attributes and their similarity of their neighbors, right? So the similarity of attributes and similarity of neighbors, you will see the Pearson correlation is it's more like positive, right? It's more like positive. And we also spot the evolution patterns in this data, which means that the graph depends on not only the previous graph. So T is not only depends on T minus 1. So for example, if you collaborated 2 years ago with someone or 3 years ago, you may also collaborate right now, but you may skip the year, right? So we find that the link that form at T, may already appeared in multiple timestamps before. So if it's just the last year, we got 60%. Yeah, it's a big number, we know. So which means that they got a repeating behavior, right? So last year they collaborate, and this year they collaborate again. However, there are still like 30% of the links that were not repeating behavior, which means they are not in the last year, but they are like 2 years ago or 3 years ago. So that's still very important to be modeled because that's 30%. And also for the triads, the links that close the triads may also show such kind of behavior like more than 2 or 3 years ago, okay? So then we have this research problem. Now how can we, given a dynamic graph sequence, how can we learn the representation of the nodes that can preserve the evolutionary, co-evolutionary patterns and perform on the task, including graph link prediction and attribute prediction? It's trying to predict the entire next graph snapshot, okay, for all the nodes, all the links, and the attributes, everything for the next timestamp. So it's a pretty challenging task. Okay, so the framework is, you can see, is try to aggregate the information from not only the previous state but also more earlier, right? More earlier states of the network, and to make a prediction. And it performed the prediction on not only the graph links but also the attributes for the X. The X are the raw features, the matrix of the raw features of the nodes. Okay, the G here, G1 to G5 are the structure of the graph. So it's trying to predict using the embedding H to predict on the left to the X and on the right to the G. So both will generate loss functions for a multitask prediction. So here is the objective functions for the optimization. The first is evolutionary loss for node attributes. Okay, the second is evolutionary loss for link prediction. And then we have the overall objective function. So some results showing that on predicting the entire next graph, or we call it forecasting a graph, and the attributes as well. So here we can see the coevergent GCN or GAT or GraphSage. They can perform better than those without the coevolutionary settings, and have a smaller error, right? Smaller error and higher AUC of F1 score, and also can beat the Evo GCN that we have introduced before. Okay, this next work is about how to model time information. The motivation here is trying to model the user behavior to predict the user attributes. So one application is like you got the, so this paper is accepted by the KDD 2020 application, applied science track. So this work is with a company that tried to, they got the behavior log of the users. And what they want to do is to predict the gender or the income of the age so that they can, based on those attributes, they can do targeted attachments. Well, those kind of private information can be missing in the database, right? People don't really want to release that. They try to infer the numbers and try to make a recommendation. Okay, but that behavior is like in their application, in the app is to see the user will read a news article using their phone. So they record the time, the news content, and the user ID and the location, right? All the kind of information. Well, here to predict their attributes, actually those attributes may depend on the spatial temporal patterns of their behavior, including some periodic patterns like the hourly patterns, weekly patterns, weekday patterns, spatial temporal patterns. For example, some businessmen, they really work overseas. They traveled from New York City to Sweden during the weekdays, and they got a time difference, and this can be periodic actually. Or some elder ladies, they may read the newspapers in the very early morning, like 6 or 7 a.m. While the young teenagers, they read the news articles at a very late time, maybe 1 or 2 a.m. So those kind of temporal behavior and also this periodic may show the difference. So also for like office, who work in the office, right? They sometimes read the news articles when they are working already after lunch, like around 1 p.m. Well, that's really for the people who live in working offices. So how can we discover this kind of patterns automatically? Deep learning is really good at automatically extracting the features. Then how can we build a deep network architecture? Then the idea is probably can take because we are interested in the patterns on hours, weeks, weekdays, then maybe the calendar can survive, serve as the architecture of the network itself, right? So we build this kind of framework that is given the input data, that user, the sessions, and the news content, and we put into them into the item embeddings layers that are the semantic embeddings of the news content, and fit into the sessions from the hours to week and to weekday. Multiple layers, and each layer it's actually we aggregate the hour of the embeddings on the hours to that concrete date, and then aggregate the concrete date to the week and to the weekday, and eventually you got the multiple attentions down there to generate the patterns and the pretty label. Okay. So on the results, you can see that this calendar gene can leverage the information in the spatial temporal behaviors to so it can outperform many other baselines on predicting the gender, income, and age of the users. Basically, for all these evaluation metrics, higher is better. And this is embedding results in a 2D dimensional space. Now you can see, yeah, pretty very well split it, right, on the attribute of gender and income categories. Okay, so last one, we just got one page to briefly introduce this work. That is, say, how can we perform anomaly detection using graph neural nets? In graph neural nets, really we do is like if we got labels for training the graph neural network parameters, that's great, right? But here for anomaly detection, for example, trying to identify the fraudsters or spammers on the social media, it's really hard to collect the ground truths. Very hard to get all the labels. However, we already have so many kinds of existing work on unsupervised anomaly detection in graph data. Even like I think the 2016 KDD best research paper goes to a work called Frauder, that is a kind of unsupervised algorithm to find the graph anomalies. So graph anomalies including two kinds of anomalies. One is graph outliers. So there are outlier nodes in the graph, or some unexpected densities, right? Very dense blocks in the agency matrix of the graph. So there are two kinds of anomalies. What we know is if we want to train the graph neural nets in an unsupervised way, we usually try random walk-based loss functions. Say if they are close to each other through a random walk, then they are likely to be similar in the embedding space. But this is not true in scenario of predicting or catching the anomalous nodes. So we are thinking about how can we use a more effective loss function to do unsupervised GN training for anomaly detection. Then actually all kinds of unsupervised graph mining algorithms, they can provide pseudo labels of the nodes for us to build a loss function to train the model, right? So here, like you can see, we can try Frauder, we can try Luck-Infer, which is working KRS 2016, and we try such kind of graph anomaly loss using the pseudo labels on the graph stage. And you can see, well, node-to-vec or graph convolution networks or even graph stage itself cannot perform very well, right? They cannot split the red nodes, which are the suspicious nodes from the majority. While if we apply this unsupervised algorithm-based loss, based on the pseudo labels, from the validation, you'll see the embedding can perform much better, right? So that's why we introduced this graph anomaly loss for GN unsupervised anomaly detection. Okay, that's all for this part. Thank you very much.
Hello, everyone. This is Chuxu. At last part, let me summarize and conclude the tutorial. In this tutorial, we focus on network representation learning using multimodal data. According to different machine learning strategies, the main content of this tutorial includes three parts. The first part is about supervised methods and applications. We introduce user and behavior modeling through network embedding and complementary learning. We also introduce heterogeneous graph representation learning for cybersecurity and health intelligence. In addition, we present some relation learning model in heterogeneous graphs, especially in academic graphs. The second part is about semi-supervised methods and applications. We talk about semi-supervised attributed network embedding. We also talk about semi-supervised graph alignment. The last part is about unsupervised methods and applications. We present some heterogeneous network embedding model and the heterogeneous graph neural network model. We also talk about graph neural network for dynamic graphs and unsupervised anomaly detection. Well, those are all the contents of these tutorials. All tutorial material, including slide and video, are available at the tutorial website. If you have any questions, please feel free to contact us. Thank you for your attendance.
Hello, everyone. We have finished all content of our tutorial. If you have any question, you can ask us directly. If not, then thank you for your attendance.